What is the hybridization and geometry around the indicated atoms? So the first thing that we are seeing, if we look at this from left to right, is we see a carbon atom. And we can see that this carbon atom has a single bond to another carbon, a double bond to a carbon. So that accounts for 3 bonds. So there should be one more bond, which would be understood to be a single bond to hydrogen. So 1, 2, 3 sigma bonds and 1 pi bond. This corresponds to sp2 hybridized. So that is the hybridization. The next thing we want to think about is the geometry. So if we draw this carbon, so here's your central carbon atom. It's got the hydrogen, and then we've got a double bond to another carbon, and then we've got the rest of the chain. So I'm not going to draw the whole thing. I just want to look at that central carbon atom. So I've got 3 electron groups. The farthest apart those can get from each other, because your electron groups are going to want to spread out or social distance from each other. And so the farthest apart they can get is to arrange themselves 120 degrees apart in a trigonal planar arrangement. So our carbon atom is sp2 and it is trigonal planar. So the next thing we want to look at is this oxygen. So we can see it is a neutral oxygen. There's no formal charge on it. We can only see 2 of the bonds. And this needs to have a full octet of electrons. So hopefully we recognize at this point that a neutral oxygen has 2 bonds and 2 lone pairs. So we need to draw in 2 lone pairs. And those lone pairs, as long as they are localized lone pairs, which is all we have dealt with so far, delocalized means they'd be involved in resonance, and we will talk about patterns later that we would see that would allow us to know if these were in resonance or not. So for now, we're just going to say they are not. So we treat these lone pairs the same way we do sigma bonds. So we've got 2 sigma bonds, 2 lone pairs, which would act the same as 4 sigma bonds. So this is sp3 hybridized. So sp3 hybridized. The next thing we want to do is we want to think about the shape. So if we expand out that oxygen, the same as we did for the carbon, and we're just going to focus on the oxygen. So we'll say, okay, it's got a bond to carbon, it's got a bond to hydrogen, and it's got 2 lone pairs. Right? And we've got the rest of the chain that we're not going to worry about. We're just looking at this oxygen atom for the shape around that central atom. And so we've got 4 groups. So those 4 groups are going to spread, if you have 4 electron groups, that's associated with tetrahedral geometry for your electron groups. But then if we want to talk about the actual geometry around that indicated atom, we only consider the angle between the atoms. So we're looking at the bond angle between the carbon, the oxygen, and the hydrogen. And so we know that all bond angles in a tetrahedron are approximately 109.5 degrees. And so all that we will see if we're looking at this oxygen is that 109.5 degrees bond angle here between the carbon, the oxygen, and the hydrogen. And so we would say that we've got just this bent shape. So the geometry here will be bent. Okay. If these were bonds, we would say tetrahedral. We don't include the electrons when we're talking about the shape, although we have to take into account the influence of those electrons. So our oxygen is sp3 and it is bent. And so that looks like option C, the carbon being sp3. No, that's not it, because it's sp3 and tetrahedral. Let's try again. The carbon is sp2 and trigonal planar. The oxygen is sp3 and bent. So it is B.